This is a video on how we're going to find the area inside a polar curve, and I wanted to start this off with just an explanation of why the formula works. If you recall from last year, if we want to find the area under the curve like this, something like this, of course we would use an integral, but we talked about last year what that integral represented. And I know we started off last year with drawing rectangles like that. And the integral really represented the sum of all those rectangles as the width of the rectangle, delta x, got smaller and smaller. And we said, well, to find the area of each rectangle, we'd take the height, which we get from the function, and multiply that by the width. And as the width gets smaller and smaller, we began to call that dx. So then it became f of x dx, and we integrated from a to b. And that was really our explanation of the integral. And there's a lot more to it, of course, and we went through the proof, but that's really what it represented. Essentially, this is the sum of all those rectangles, where f of x represents the height of the rectangles, and dx represents the width of those rectangles. So moving on to polar coordinates, this is a little bit different because we don't use rectangles. So let me start by drawing a little sliver like that of this circle. Now if you recall, we're going to call this theta. If you recall from the beginning of calculus and pre-calc and geometry, arc length, this length right here, we get from a formula, we call it S, and it's the radius multiplied by theta. And of course, the radius is r. Now, the idea here is that as these triangles are fit in and they get narrower and skinnier like that, that these edges really begin to become straighter. Essentially, going back to what we talked about with derivatives and with integrals, that the smaller you get, the more it looks linear. So essentially, these little slivers, these little pieces of the circle begin to look like little triangles fit together. The smaller these little slices become. And they have a area of 1/2 the base, which we called r theta, multiplied by the height, which is r. Well, of course, in this case, theta is getting smaller and smaller, so we say, well, 1/2 r delta theta multiplied by r, because we want these thetas, these angles, to get very small up here. Well, as we move towards integrating, then similarly to before, when the delta x became a dx, now the delta theta will become a d theta. So r times r is r squared, d theta, and we will integrate. This is another picture of a polar graph, and I just wanted to explain why the same idea works even though it's not a circle. We're still going to fit triangles in. And again, this really looks like a triangle. Okay? And we've got the radius r, which of course comes from the equation. It's how far away from the origin we are. This length right here we kind of assume is circular, and we call that r theta. So you see, even though it's not necessarily a circle, as we build these triangles in, it still takes on the same types of shapes. So the area inside a polar curve can be achieved. I like to pull my constant coefficients out, so 1/2 times the integral of r squared d theta. That is the area of a polar curve. The one thing that maybe makes this tricky, or in my view more interesting, is because this is d theta, because all we care about is theta in here, that's what sets those the base, then the bounds have to be in terms of theta. So here's a quick example with r equals 3 sine 3 theta. I want to find the area bounded inside this 3-petaled flower. Okay. Now, if you graph this, this right here is 0 to pi over 3. This is pi over 3 to 2 pi over 3. And this is 2 pi over 3 to pi. So you really trace the entire thing with just going from 0 to pi. Now there are lots of ways to figure that out. I'm going to talk about that later in a video, but essentially it really is then as easy as saying, well, the area is 1/2 3 sine 3 theta squared d theta. And since the bounds, since we talked about the fact that to get from the first loop around the second loop, around the third loop, and back to the beginning is just 0 to pi, that becomes our bounds, 0 to pi. Don't just assume that every polar shape is 0 to 2 pi, because very often they're not. I mean, they are sometimes, but don't just assume that, because of course in this case, if you went from 0 to 2 pi, then you would begin retracing, and you'd actually end up with double the area you wanted.